So TR-Rosetta results page will looks like this. Uh, at the top, you will see the job ID and the name of your protein. So your protein in this case, and the modeling results are available for download, including the primary model and the other lower ranked models. Okay, model 2, model 3, model 4 and 5, and additional data such as multiple sequence alignments were also here. This ribbon structure represents the predicted 3D model of your protein, and this help visualize the progression of the polypeptide chain along the sequence. Here a TM score is provided below this structure image. So TM score, it is a measure of structural similarity between the predicted model and the true native structure if available. Okay. A score above zero point 0.5 indicate the prediction is likely to have the correct topology. Here the TM score is 0.958, which indicates a very high confidence in the predicted structure. Okay, then this graph on the right plots predicted per residue LDDT scores against the protein structure position. So LDDT score evaluate the accuracy of each residue's position in the predicted model compared to a native structure. And its score ranges from 0 to 100. So scores above 80 are uh, considered highly accurate, and scores between 50 to 80 indicates a moderate accuracy, and scores below 50 suggest low confidence. And in this graph, the majority of residues have an LDDT score above 80. So this means that most regions of the model are highly accurate, and there might be a few dips in the graph. This indicates some regions with slightly lower confidence. So the confidence of this model is very high as confirmed by deep learning methods and homologous templates. So this predicted structure can guide functional studies, drug design, or protein engineering further. So using these LDDT scores, you can pinpoint reliable regions uh, for experimental validation or docking studies. So TR-Rosetta provides a reliable prediction of protein structure with confidence matrices like TM score, LDDT, etc. So a high confidence regions can be prioritized for downstream applications, while low confidence areas might require experimental validation. Next, we have a series of heat maps here under the title Predicted Inter-Residue Distances and Orientations. And these maps represent predicted 2D informations by TR-Rosetta using deep learning. Okay, first one is contact map. This shows which residues in the protein are close to each other in space. And the axis represents the residue numbers, and each point on the map correspond to a pair of residues. The color intensity from light to dark red indicates how strong the contact prediction is. Darker color suggests stronger confidence in the residues being in close proximity. And this map is critical for understanding the overall folding of the protein. Next is a distance map. The Instead of just showing contacts, this map gives the actual predicted distances between the residue pairs. The axes are the same, means the residue numbers, but the colors represent the predicted distances. Red and orange for shorter distances, yellow for moderate distances, and white for larger distances. So this information helps to fine-tune the 3D structure of the protein. Then omega, theta, and phi. These three heat maps represent the orientational information between residue pairs. Omega map predict the dihedral angles between the residue pairs, specifically the angle around the bond connecting two residues. This red area represents specific angular constraints between the residues. And in theta map, this shows the angles between residue pairs related to a reference axis, which is important for capturing backbone geometry. Again, the colors represent angular relationship with the red and yellow indicating specific angle predictions. And this phi map, it represents another dihedral angle between residues but involves a different geometric relationship that omega. Like the others, this map helps capture the spatial orientation of residues. So together, these three maps means omega, theta and phi describe the angular constraints that define the 3D conformation of the protein. Then below the heat map, you will find a section titled Templates used by TR Rosetta. So here the first column shows the rank of each template. The rank indicates how well the templates matches the query sequence with the rank 1 being the best match. Then template. The second column lists the template ID which correspond to non-protein structures from this PDB database. So clicking on this IDs will take you to the protein data bank entry for that template. And then confidence. Confidence indicate how confident the algorithm is in selecting this template. So a confidence of this 99.7 means this is a highly reliable match. And then coverage. This refers to the fraction of the query sequence that aligns with the template. Higher coverage means a larger portion of the sequence matches the template structure. Okay, next is identity. So it represents the percentage of identical residues between the query sequence and the template. And e-value, it tells us how statistically significant the match is. Smaller value indicate a highly significant alignment. Then we have this Z score. It evaluates how well the template align with the query compared to other possible templates. Higher Z score indicate better matches. Then we have this modeler column. It provides links to download the model based on this template. Okay, then we have this predicted secondary structure on the right side. The structure is annotated with the helix, strands and coils. And this gives us a quick idea of the structural elements in the predicted protein model. So that concludes our discussion on the TR Rosetta results. Okay. So one more thing, these templates were detected by running an HH search algorithm against the PDB70 database. So HH search is just a bioinformatic algorithm. It compares your protein sequence or MSA to a database of non-protein structures, and it will find a potential templates for structure prediction. And then it calculates how well the query matches each protein in the database and assigns scores like this confidence, e-value and coverage to help decide if a match is worth using as a template. Okay, so that's all about TR Rosetta. So TR Rosetta is really a jump for protein structure prediction that continues to improve daily. Notably, it ranked first among other protein structure prediction methods in CAS16, so demonstrating its exceptional capabilities. So as TR Rosetta advances, it is poised to revolutionize the field of protein structure prediction.